Welcome everyone in presence and in remote. I think this is the 41st MARVEL Distinguished Lecture, and it's a great pleasure to have here a long-term colleague and friend, Professor Hannes Jonsson, currently at the University of Iceland, also sort of basically back in the home country. Hannes actually got his bachelor in chemistry there, and then he moved on to do a PhD at the University of California, San Diego. And after, say, a postdoctoral stay at Stanford University, he moved to the University of Washington in Seattle, where he was there for many years, actually sort of starting only back in 2000 to be sort of both in Iceland and in Washington, and from 2005 definitely in Iceland. So in Seattle, he was the full say tenure scale assistant associate, full professor, and that's I guess when we first met, when we were both in the US. Of course, everyone knows Hannes for his work, in particular on the nudge elastic band and the climbing image and nudge elastic band, but in general, in a lot of topics on physical chemistry. On a more personal note, is one of the few other people in the world with which we interact on self-interaction and orbital density-dependent potential. He was telling me that these days also he uses some of these ideas from the nudge elastic band to look at electronic state rather than atomic state. And so today we'll hear his latest work on calculation of excited electronic state using saddle point searches and self-interaction corrected density functional with comparison to neural network selective configuration interaction. Hannes, fantastic pleasure to have you here. Please.
Thank you. It's truly a pleasure to be here again. And I look also forward to the defense here later on today, but I understand that's a closed oh, I see. I misunderstood. I dressed up in my white shirt and everything, but it's okay. Good. So yes, saddle point searches. We have been working on finding saddle points and minimum energy paths for a long time, now 30 years, I think. And that has been in the context of finding mechanism and estimating rate of atomic rearrangement, like chemical reactions, diffusion events, conformational changes. So the atoms are moving, and we want to find then saddle points, the first order saddle points for on the energy surface, describing how the energy of the system is varying as a function of the atomic coordinates. Now I'm going to tell you about another use of these methods and a little bit of an extension of those methods to find excited electronic states, and that may come as a surprise. But if you think about a different energy surface, namely this one here, which is the energy of the system as a function of the electronic degrees of freedom. So let's say you have, a linear combination of molecular orbitals that you use to describe your wave function, or whatever, linear combination of Gaussians or plane waves or whatever. So you have here some electronic degrees of freedom as the x and y coordinates, and then you map out the expectation value of the Hamiltonian, the energy of the system for all of these different wave functions. And then that is going to map out an energy surface that we call an electronic energy surface. And sure enough, the minimum here is corresponding to the ground electronic state. But what I'm saying is that the saddle point, here's a first order saddle point, and here's a second order saddle point if you have this in a higher dimensional space. They correspond also to solutions of the underlying equations. Using the generalized variational principle, if you have a function which is such that any infinitesimal change to this function doesn't change the expectation value of the Hamiltonian, then you have a solution to this Schrödinger equation. And same thing here, if you have a Hartree-Fock or density functional calculation, if you have a set of orbitals such that any infinitesimal change in any of the orbitals doesn't change the expectation value of the Hamiltonian, you have a solution to the underlying equation, either Hartree-Fock equations or the Kohn-Sham equations. So these are indeed solutions to the Kohn-Sham equations if we stick to DFT. They are of higher energy than the ground state, and so they are technically excited state solutions to the Kohn-Sham equations. Now you might ask, well, geez, Kohn-Sham density functional theory, or density functional theory in general, is just a ground state theory. What am I saying here? Well, let's see how it works. So the way to find this variationally optimized set of orbitals is then an exercise in walking on this energy surface and converging onto the saddle point, and the saddle point of the right order. Okay, and we will see that it is a very important principle that you want to know what saddle point order you should be converging on and following as you change the geometry of the molecule. That gets to be a principle for navigating on this complex energy surface, which of course has a lot of degrees of freedom, right? High dimensional, so it's important to have some way of navigating through it. By the way, ask me a question anytime you like. You know, I have a long list of slides, and we'll see how far I get. I would much rather have a nice discussion with you and not get through them all. Fine. Okay, so I put here a picture of a mountain that's close to where I live. So I took this picture when I was walking the dog some time ago. This is Snæfellsjökull. As you can see, finding electronic excited states is a little bit like walking on a mountain. You know, you want to find mountain pass or mountain peak, and that will give you a solution to the equations. By the way, this is the volcano where Jules Verne had the journey to the center of the Earth start. They went down here, explored the underworld, and then came up in Stromboli. Right. Okay, so now of course it's very important to also be able to test, you know, are these solutions we get for excited states using this principle any good? How can we compare them to something that we really know is correct? So we've also been doing selective configuration interaction calculations, then using neural networks to help speed up those calculations so as to get estimates that we really believe and can compare with these other ones that we obtain from density functionals. Now, applications that I'm going to talk about are, first of all, the twisting of the double bond in ethylene. That's the active ingredient in molecular motors, and charge transfer excitations in molecules. Then I get to solid state. I know here most people are interested in solid states rather than molecules. I'll talk about charge transfer, about the nitrogen vacancy defect in diamond, and the lithium substitutional defect in magnesium oxide. And then get back to molecules. Rydberg states are particularly difficult states because they are very, very diffuse. The electron is very delocalized, really. And so it's a very hard calculation for atomic basis sets. So that's, since we are using a solid state code, we can represent these diffuse states much more easily with plane waves or with finite real space grid. And so I'm going to get back to that. And that's also where I'm going to show you some results of the selective configuration interaction calculation. So we actually had a group outing out on top of the volcano here. And this is Alexei Ivanov, who now is working in Cambridge at the quantum computing company. I'm going to show you a few more pictures from that later. All right, so let's get back to this electronic energy surface. So make sure we all understand what is going on. Let's take our favorite molecule, and as an example, hydrogen molecule. Use the simplest basis set, just the 1s orbital, atomic orbital on each one of the atoms. And so it's a minimal basis set calculation. Let's go and conform the molecular orbitals instead. So the bonding and the anti-bonding molecular orbitals, and use those as the basis now for any wave function that can be constructed with this within this space. Now, of course, the ground state is going to have both electrons here on the bonding molecular orbital, a symmetric spatial function, but then an anti-symmetric spin function, one spin up and one spin down. So that's going to be the electron configuration of the ground state. But we can basically formulate 4 different orbitals from this. And for the occupied spin-up orbital, we want to have both electrons in the bonding orbital. So we can, but more generally, we can say we're going to have some linear combination of the bonding and anti-bonding orbital for spin-up. So, and since we want to keep a normalization, we just write this as sines and cosines. And then we have an unoccupied orbital for spin-up, which will be orthogonal. So we can write that as minus sine and cosine. And then we have the spin-down orbitals, the occupied one and the unoccupied one. And these are going to be some linear combinations of the bonding and anti-bonding spin-down. All right, so these are the 4 orbitals we can generate from this basis. And now we can evaluate the energy. And it is going to be a function of these two parameters. There's a parameter phi alpha for spin up, and there's a parameter phi beta for spin down. It's just two parameters for all these different wave functions we can generate from the spaces. And we can calculate the expectation value of the Hamiltonian for all of them. And of course, as I mentioned before, the minimum here is going to be the ground state, corresponding basically to the two electrons being in the bonding orbital with spin up and spin down. But then we have these first order saddle points. And so let's take this one, for example. We have here that phi alpha is equal to 90 degrees, while phi beta is still 0 degrees. And that means we have actually put a spin-up electron into the LUMO, the antibonding orbital. So this saddle point here corresponds to this configuration of electrons. These other first-order saddle points here are equivalent. This would correspond to having the spin-down electron in the LUMO and the spin-up in the HOMO. And then these are equivalent just by -1. Okay. Now then we have also these second order saddle points, and they correspond to, let's say, phi alpha and phi beta both being 90 degrees. And that means that we are taking these, basically putting both the electrons into the LUMO. So the antibonding molecular orbital. So that sort of relates these stationary points here to different electron configurations. Yes? Yes, right. Very good. Yes, so first order saddle point has one negative eigenvalue in the Hessian. So the Hessian, the matrix of second derivatives, has one negative eigenvalue. And so in here, for instance, there is only one mode for which this is a maximum, and it's a minimum for the other mode, the orthogonal mode. That's a second order saddle point because there are two negative modes in two directions. All right, very good. Thank you. Okay, so now let's take this molecule and start stretching the bond. And sure enough, we see here the molecular, minimum. The optimal distance is here, the bond length. And then we stretch it a little further, and we get to a point, so-called Coulson-Fisher point, where in fact it is advantageous to break spin symmetry and to allow spin up electrons to be the spin up electron to be in a different place than the spin down electron. This is really essential for getting a dissociation into two separate hydrogen atoms. If you don't do that, if you stay with a spin symmetric solution, you get the so-called ionic terms. You get too high energy. This is seen very nicely in the topology of the electronic surface. You see what happens, for instance, at this point here, beyond the Coulson-Fisher point, the topology changes. What used to be the position of the minimum is now a position of a first order saddle point. And you need to roll down the energy surface here down to this minimum or to that one, corresponding to either this solution or that solution. So this Coulson-Fisher point comes very nicely into, becomes obvious from the topology of the energy surface. And this is becoming then a general principle. If we want to find a minimum, we have to have all positive curvatures, right? And so we would recognize then at this point here, we're not at, we have one negative curvature. We need to move. We need to move down to here or there where we have a minimum, a 0th order saddle point, if you like. Now, in this case, it's also very easy to see. I mean, we just want to, if there's a bifurcation here, we have two solutions, and we want to pick the one that's of lower energy, right? So that's pretty simple. I mean, you've done this calculation. I'm sure you just have to break a symmetry, and you get to this broken symmetry one. But you're doing something slightly illegal. You don't have an eigenfunctional spin anymore. So this is something that comes when you're confining yourself to a single Slade determinant representation. You do sometimes break symmetry and get better solutions that way, although they're somewhat illegal. All right, so let's go and take the first order saddle point here and follow that. That's just this green repulsive curve here, not too interesting. But let's now go to the second excited state, which starts out here with 90 degrees over here. And then we follow that. And again, there's a symmetry breaking point. It is a spatial symmetry breaking point, similar to the Coulson-Fisher point. And if you're not careful, you can see at this distance here, what used to be a second order saddle point has turned into a first order saddle point. And that's bad news. We should follow a second order saddle point. So we need to move now from the 90 degree solution to here. And that's the curve that actually properly has a minimum, and that's the right curve. And so in this case, we don't choose the lower energy solution of the two. We actually need to choose the higher one. We need to choose the one that has the right saddle point order, illustrating how that's the principle you have to follow in finding which solution to accept. So in general, of course, one would like to be able to do dynamics on an, yes. Why? Sorry. Yeah, we need to stick to the second order saddle point. If we don't, we are basically falling down here to the ground state. If we allow us to stick on the first order saddle point. So that this doubly excited state corresponds to a second order saddle point. And we better we better convert onto a second order saddle point. And it's a danger, of course, if we just feed in the solution from before. We are stretching the bond here as one step at a time. And if we just feed in the previous solution to the slightly longer bond length, we would indeed find a solution here. It's a danger that we would actually slide down here. And that is often the case with so-called delta SCF calculation. This will be under the big umbrella of delta SCF calculations for finding excited states. But this one is that I'm presenting to you is different in that we are really paying attention to the saddle point order that we're converting on, and can see the danger of just taking some solution. All right, good. Thank you for your questions. Okay, so yeah, in general, of course, we are interested in doing dynamics on excited state surfaces, improve solar, harvesting, and so forth. And so we are looking for a cheap method that we can use to calculate, evolution of the system on excited surfaces. And of course, this is a beautiful picture from Basile Courcade, and I like to show that. There are these very important points here, so-called conical intersections. That's where the two surfaces, the excited electron surface and the ground surface, come together and kiss at a point. That's where it's most likely to have the system is most likely to go between the surfaces, and they are particularly important. Now, of course, often these systems are very big, solvated, complex, and so forth. We use, QMMM representations and so forth. Here's a recent paper where we did that, but I'm not going to get into that here. Okay, I'm going to stick to simple systems. Let's take this simple ethylene. Ethylene has that carbon-carbon double bond, and so you can you raise the energy by twisting it, but then at the same time the other end here, it tends to pyramidalize. So you can describe this in 2 degrees, the twisting angle and the pyramidalization angle phi. And here is shown the energy difference between the ground state, this is called N, and the V state, that's an excited state. And that's the contour plot of the difference between the two. And so we can see here they kiss, and that's the conical intersection. The region where they are within half an EV, which is pretty close, it's sort of the cyan color here, and then you have these other contours here, 1.0, 1.5 EV difference between the two. This is just a simple PBE calculation, very, very simple, GGA functional. I should note that one has to take into account here, this is an open cell singlet, this excited state. So there is a so-called spin purification formula here. Namely that if you just do a single state determinant calculation of this open cell singlet, you get a mix of the true singlet and the M equal to 0 triplet state. So you need to undo that. All right. Now, here's a high-level multi-reference CISD calculation. It's a big calculation. It's a lot more difficult calculation that scales much higher with in computational efforts with the number of electrons. You can see that the two are very similar. We actually get this conical intersection pretty well. On the other hand, if you use something like the most common tool, which is the linear response time-dependent DFT, you do not get this conical intersection. You can actually show mathematically you can't get the conical intersection right and with that theory. And this is with a B-lip functional. If you go to B3-lip, it's a hybrid functional, you actually get a negative gap. I mean, the excited state actually becomes lower than the ground state there. So you can see that linear response time-dependent DFT is notorious. Most people know that you cannot really get conical intersections with that method. So let's go to the second excited state. It's called Z state. And that's similar to the what I showed you before for the second excited state of the hydrogen molecule. Here's the ground state geometry, and we have a very high energy here. Now, as the molecule starts to move on that excited state, it's going to rotate. And so it naturally rotates down to here, about 90 degrees. We have to be careful. There's a spatial symmetry breaking point here. So you can slide down to the first order saddle point, if you're not careful, this is color coding here, the value of the second eigenvalue going negative here. But you have to stick to the second order saddle point, then you get this curve here. And as I mentioned, this is an element in molecular motors. The molecule rotates down to here, and then it comes down to the ground state. There's the ground state here, and then it completes the half a circle, 180 degrees. One photon, half a circle, another photon to complete the circle. Anyway, this is the comparison with the multi-reference calculation. You see that our gap here for the avoided crossing is a little bit too low, but the shape is really pretty good for a very, very simple calculation with a PPE functional. Yes? Absolutely, yes. I will get to that. So, well, very good, thank you. Okay, but then there are other states, and so here's a summary of several of these states. Here's the V state. Here's a Rydberg state that actually comes in also. And then there's the Z state. So you can see qualitatively, the comparison with multi-reference CISD is pretty good, but then, Nicola, with self-interaction correction, the agreement is amazingly good. And you can see the Rydberg state actually comes in and is the lowest excited state, is the first excited state for the ground state geometry, not the V state that I showed you before. And that comes out right. So it's a very nice result. It was published in 2022. Okay, so saddle point. Saddle point, of course, is difficult to convert on because there's a tendency, if you use a normal algorithm for getting to a self-consistent solution, you have a tendency to go down to the minimum, right? And as we mentioned before, if we have an nth order saddle point, the Hessian has n negative eigenvalues. So what do? Well, we basically use what we have been doing for a long time. You see, this is the problem. We are looking here at the force, or the negative gradient around the first order saddle point. And you can see some of the arrows are pointing towards the first order saddle point, but some are pointing towards the minimum, the blue minimum here, or the blue minimum over there. So that's the problem when you use this in let's say a steepest descent or whatever conjugate gradient or LBFDS, you will tend to go to the minimum. So what do? You need to find the eigenvalue, or you need to find the eigenvector corresponding to the lowest eigenvalue and only the lowest eigenvalue somehow. And if you can get that, the so-called minimum mode, then you can make a transformation of the gradient. So you just reverse the component of the gradient in the direction of the minimum mode. You project onto the minimum mode and multiply by the minimum mode and the eigenvector of the lowest eigenvalue and subtract. And then you transform these black arrows into the red arrows. And so now all the arrows here are pointing towards the first order saddle point. So if you take this modified gradient, you plug that into your steepest descent or conjugate gradient or LBGFDS, you converge onto a first order saddle point rather than a minimum. It's as simple as that. And this is an old trick that we presented, and it's used in many different flavors, but this one that we like, minimum mode following, we presented in the last millennium. And it's basically like this, if you have a negative eigenvalue, do this transformation. If you don't have a negative eigenvalue, you're still too close to the minimum, then climb uphill along the minimum mode. And that sort of shows a few of these searches here. This is an energy landscape. We have a minimum here. We have 4 different saddle points. Depending on how you initially displace and then convert, you get to different saddle points. For every starting point, there is some saddle point that's closest. There's some basin of attraction. So that's shown here in the light gray. The basin of attraction to saddle point 1 are all these points here that are light gray. The basin of attraction to saddle point 2 is here, and 3, and so forth. So depending on where you start, if you now say, I'm going to converge onto a first order saddle point, depending on where you start, you will converge onto saddle point 1 or 2 or 3 or 4. Okay, I'm getting to your answer a little bit, not step by step, all right? So it's clearly very important that we start close enough to the saddle point we're interested in. within the basin of attraction of that saddle point. Now, we need to generalize this then to higher saddle point orders, and that's so-called generalized mode following. So if we want to converse on to an nth order saddle point, we just need to find the n lowest eigenvalues of the Hessian, the corresponding eigenvectors, make the transformation of the gradient along all those n eigenvectors, and then plug that into your optimization routine. If you don't have n negative eigenvalues, then move uphill until you get to n negative eigenvalues, and you just get into the basin of attraction of an nth order saddle point. Yes, Rohit? Strictly not. Strictly not. This is assuming you do a very careful job, But if, of course, you may be, you may have a too aggressive optimizer, and in which case you may cross a boundary, right? Yes.
This is always around minima, right? So like minima, this is always be away from the ground state.
Yes, right. That's right. So with this algorithm, you don't have any danger of collapsing to the ground state. Now there are very nice algorithms, so-called maximum overlap methods, due to Peter Gill and coworkers in Sydney, that have been used to converse onto excited states using density functionals, for instance, or Hartley-Fock. But they do have more of a, they do have in some cases the danger of collapsing down to the ground state. This one does not. Very good. Okay, so let's take another example. Don't you have a question?
Necessarily improve they converge to a physically meaningful state, or not necessarily?
I don't have a proof that it will necessarily converge onto a physically meaningful state. It depends on how you're describing a system, I would say. If you are describing the system with configuration interaction, you are guaranteed, yes, that's going to be a meaningful state. I will get to it a little later. If you're doing this with a density functional, well, all bets are off. Okay. All right, let's take another example. Here I'm getting closer to your the answer to your question, actually the previous one. So let's say we are interested in a charge transfer excitation in this molecule. This is a molecule that has two rings. There's a it's a pyrrole ring here and a phenyl ring there. And this is just showing the ground state calculation. These are the orbital energies. And you can see here the orbitals. And you can see the HOMO has the electron mainly here on the pyrrole ring. And then if we go to the LUMO, the electron is mainly here on the phenyl ring. So a HOMO-LUMO excitation that looks like a HOMO-LUMO excitation would bring the electron from the right to the left. That's a charge transfer excitation. Those kinds of transfer excitations are particularly important for harvesting photons, because you need to separate the electron and the hole, right? So charge transfer excitations are particularly important. So let's say we want to find this excitation here. So we do that. So we take the electron out of the HOMO, stick it into the LUMO, freeze those two orbitals. Now we need to move close enough to the saddle point we want, okay? So we freeze those two, let all the other orbitals relax, so because they are now seeing quite a different environment, right? Their mean field interaction is quite a bit different as this electron has moved so much. But they are optimized then. And then we look at the Hessian and use Davidson to find the lowest eigenvalues. And we find 7 negative eigenvalues for this. So it looks like not a first order saddle point, like we would think perhaps for a HOMO to LUMO excitation. It has 7 negative eigenvalues. And you're never quite sure. So you have to try, plus minus 1, 6, and 8. And it turns out this ends up being a 6th order saddle point. See how much the orbital energies have changed going from the ground state to the converged 6th order saddle point solution. We still have that the electron has moved from left to right, from right to left, sorry. But you see this what used to be the HOMO is now down here. And so forth. So the orbital energies have been changing a lot. But we can see this as a 6th order saddle point. See how many negative modes there are for the system. How many ways are there for the system to go down now in energy? You have this electron. This is just one of the spin channels. Of course, the other one is unchanged. This the electron could go down to here. That's one. This electron could go down. That's one. 3 modes here, and then here 4, 5, 6. There are 6 ways for the system to lower its energy by taking an electron from this configuration to a lower one. So it's a 6th-order saddle point. Now, how good is this? The calculated excitation energy is 5.39 eV. The estimate, reference energy estimate from Pierre-François Luz in Toulouse is 5.58, within 0.2 EV. How, you can't get any better with a density functional, right? So it's providing a very accurate and meaningful answer here. But so I think I've answered this for you. So we need to basically start with the ground state calculations, identify what electron transfer we want from what orbital to what orbital, right? Once we freeze those and relax everything else, so to allow the system to cope with that change, and then we let it go. We estimate the saddle point order, and then we let go. All right.
So I guess there's no way to study the correlation of first order saddle points between the excited state or second order saddle points.
Not within density functional or Hartree-Fock. There is, however, I will get to it. Within configuration interaction, there is a strict correspondence. Configuration interaction is just a linear expansion in slated determinant. So it's a linear theory. So you can work this out very nicely. The first excited state is a first order saddle point. The second excited state is a second order saddle point, and so forth. But when you're doing Hartree-Fock or density functionals, well, that's a nonlinear optimization, and you are constrained in many different ways. You see, if you have a third order saddle point and you're taking out some degree of freedom, that may turn into a second order saddle point because you remove some flexibility. We can go back to this thing here, the hydrogen molecule, for instance, and see here, you know, if we were to confine ourselves to spin restricted DFT or density functionals, then this two-dimensional plot would be constrained to one dimension, right? Because it's phi alpha and equal to phi beta for the spin pairing, and that means you just have a line here, and this first order saddle point turns into a minimum. As an example of how a constraint can lower the saddle point order. Okay. Okay. So. All right, so I think I've explained the method roughly. This is implemented in GPO. This is a grid-based PAW code that is largely developed in the Nordic countries, started in Finland and Denmark, and also in Iceland now, and some other places. We like it because it's mostly Python-based. We do this with direct optimization and so forth. Here are some very important papers on the method we use, and this has been extended to self-interaction corrected functionals, namely, you know, orbital density dependent functionals. And this is now also the default method in ORCA, the Gaussian-based code that is used by chemists mainly. And this is the default time-independent way of calculating excited states in that code. This is also now in the main branch of GPO. Okay. All right, let's go to a solid state example. So that's the nitrogen vacancy defect in diamond. You've taken one carbon atom out and put a nitrogen atom instead, and there's a vacancy right next to it. And so you have 4 electrons. Now there's an extra electron with the nitrogen, and there are 3 electrons here that are thinking, you know, what are we going to do? There are 4 electrons that go into the gap states there, and it's pretty well known that there is there's an optical cycle for preparing a pure spin state here. You will go from the ground triplet state to an excited triplet state. Then there's intersystem crossing to an excited singlet, and then that can go down to a ground singlet state, and then intersystem crossing again. And when the system comes from the singlet to the triplet, it only goes to the M-0 sublevel. So this, by going through this cycle here, can be done at room temperature. You can prepare a spin pure state here, and it lasts for a long time because it's in the gap of diamond, which is a rigid material, and so forth. So this is used for all kinds of quantum technologies. How did people come to know about this? Why is the nitrogen vacancy defect in diamond to begin with, very interesting and important. And lots of money has gone into studying it. Exactly. It's a way to distinguish a real diamond mined in South Africa from a synthetic one. That's a very important practical problem. That's why we know so much about this defect. But then it turns out to be very useful for quantum technologies, perhaps even quantum computing. Now, one would, of course, like to see, are there some other systems that the diamond company in South Africa is perhaps not so interested in that may also be, or even better, for quantum technology? Can we use density functionals to search for other systems that might be of interest for quantum technologies like this? So this is a calculation we did. It was Alexei that I mentioned before. He was the one who was working up the mountain there, and now is in Cambridge at the quantum computing company. And these are calculations with 512 atoms in a supercell. I'm going to show you here calculations with a few levels of density functionals, and we're actually now doing the self-interaction corrected calculation. I'm going to show you, not going to show you, we know that band gap is coming out very well there with HSC06 also, but the experimental band gap is 5.5. We have 4 electrons that need to find their place in these defect states in the gap here. And we calculate these. So here's the ground state triplet. Here's the spin up and spin down channel. And we have the excited triplet state and the lower singlet and the excited singlet. Then to find the proper many-body wave functions, we have to take the right linear combinations of these saddle points. Just like we said, for the open cell singlet, we need to do the spin purification formula, and a similar thing for the excited singlet here. I'm not going to go into that, but these are calculations we convert onto these. These are all different saddle points. And here's our result. So depending on what functional we use, we indeed get very different levels especially for the excited singlet state, but also somewhat for the excited triplet and the lower singlet state. But these they all have the right ordering. This is different from some previous reports in the literature showing that there was incorrect ordering coming from density functional calculations. So in fact, there are big statements in the literature saying that density functionals cannot be used for this problem at all. But now it's actually seems to be working quite well. And we can compare here with experiment as much as is known. The excited triplet state is a little bit too high, perhaps by 0.1 eV. And then here's the excited singlet that's a little bit too high also. But and here's the lower singlet. But then with relaxation, here we can calculate, because now we get the forces. We have variationally optimized wave functions. So we have Hellman-Feynman theorem. Hellman-Feynman theorem working for us. We can calculate the forces, and here we relax in the triplet state. We see how much it's decreased, and that is in good agreement here with experimental estimates. And here in the singlet, lower singlet state, we get a relaxation of 0.07 eV. Now here are some other calculations. This is from Julia Galli. I was going to be giving a talk here tomorrow, receiving the CCAM prize. This is, I believe, the most accurate calculation. It's embedded beyond RPA calculation. It agrees very well with the R2 scan, but there's somewhat lower results than lower values than the HSC06. But then there are also, here's a quantum Monte Carlo calculation. It seems to suffer from the fact it's done for a cluster. Anyway, there are lots of calculations of this defect, but our calculation here with a saddle point search and the hybrid functional, or even with the R2 scan, is actually in pretty good agreement with the experiment. Now I'm going to show you another example. How am I doing with time? Oops. Okay. Can I do 10 more minutes or okay? Let me show you another solid state example, one where the HSC06 doesn't really work that well. And that's the lithium substitutional defect in MgO. So you've taken out a magnesium atom, you put a lithium atom instead. And so there's one electron missing, right? And so you have a hole. And so one of the oxygen neighbors of the lithium atom is missing an electron. So you have a spin density here that sort of looks like a p orbital, right? Because there's a p electron missing in the lone pair of the oxygen atom here. This has been studied a lot with spin resonance and so forth. In the 1970s, people already had pretty good idea that there is one of the lithium-oxygen bonds is lengthened by about 14%, and the spin density is located basically on that oxygen atom. And this creates a defect state in the gap. It's about 1.8 eV above the valence band. So this is all deduced from spin resonance and some modeling of that. Now, if we do a calculation with a simple PBE functional, with DGA functional, which I've been using here so far, you don't really get very good agreement. You get, of course, a band gap that's way too small, and the defect level is here in the top of the valence band. If you go to HSC06, it still isn't very good. The spin density is delocalized over all 6 oxygen neighbors of the lithium atom, not just one. And so there's a lack of localization here that should be there. And you can see that the band gap, of course, is better, but not quite as good as this experiment. And the defect level is only 0.4 eV above the valence band edge. Oh, yes, and I should say there's a paper here from Berlin saying that, well, the experiments must be wrong. HSC can't go wrong. Anyway, with the SiC, we get a nice band gap, and the defect level is 2.1 eV above the valence band, and there's the spin density is localized on one of the oxygen atoms. The oxygen lithium bond is lengthened by 11% rather than 14%. So it looks really, really nice. And very recently we got also the excited state. Now this is, of course, deduced from luminescence, really, or the fluorescence, I should say. People excite MgO, and then they see light coming out from this defect state. The excited electron jumped onto this defect state and emits a photon. So this is just the orbital energy. That's not really telling you what the energy of the excited state is, right? So when we calculate the excited state, it actually is 1.5 eV above the ground state. And you can see here, this is the ground state with the spin density on the neighbor of the lithium atom. And here we have the spin density on a hole that's further away from the lithium atom. And the energy difference is about 1.5 eV. All right, finally, I'm going to get to the Rydberg excited states. Rydberg excited states are such that you have a very large distribution of electron. It's very delocalized, well, quite a lot. So this is the this is the HOMO of ammonia, and this is the 3pZ Rydberg state. You can see how much this is the same value here for the orbital in the visualization. You see how much distributed it is. Now here we calculated the excitation to various Rydberg states. These are the first excited states of ammonia are actually Rydberg states. First one is a 2s state, and then there's a triplet 2s, and then a triplet plus minus, and a triplet PZ. And you can see for various different functionals, we're getting results that are pretty close to the experiment. The blue line here, the blue bar is the experimental value. And PBE with SiC is giving us the green line here. That's really good. But even PBE without SiC, and this is remarkable, because when you do the PBE calculation, the unoccupied states are not bound. If you put an electron there, you would say, hey, the electron just leaves, because the long-range form of the potential is wrong. But when you put an electron there and you converse onto a saddle point, you actually get pretty good results, even with PBE, remarkably. By occupying this state and self-consistently converting and variationally optimizing the orbitals, you actually get the really good results. Now here's TPSS and R2 scan. They give very similar results. So it's really not much of a change. The key thing here is to get the right long-range form of the potential. Now here's a high-level quantum chemistry calculation, extrapolated full CI with this basis set. And you see it's giving a lot larger estimate of the excitation energy by about 1 EV. And so is this correct or not? Well, when I first showed this to people, they said, well, there are all kinds of corrections to the experiment. You shouldn't take the experiments too seriously. There are 0-point energy corrections and who knows what. You have to go from, there are ways of, interpreting the experiments, right? So we really had to go and do a better calculation. And but anyway, let me just show. We have done several other Rydberg calculations. Alec did his master's degree on this and master thesis, over 30 Rydberg states. With PBE, we get with 0.2. With PBE and SiC, we get amazingly good agreement. for Rydberg states. Now, but these are very difficult to do with atomic basis sets. We are using plane waves or finite real space grid, so it's no problem in representing the highly delocalized states. Okay, so we need to get a reference here. We need to see what is right. And so we do configuration interaction. That's a simple linear expansion of all the slated determinants you can form. And normally you do the ground state slated determinants that you use them here. Now, of course, most slated determinants are not important. Here's a calculation of N2 from a few years ago. And you can see here the magnitude of the coefficients in this expansion. And the sum of so the first three saddle points, sorry, the slated determinants give you a sum of about 0.9. That's almost a full set. But then you go out and you go here to larger and larger, smaller and smaller magnitude of the coefficients. You can see that once you get out to here, there's almost no contribution. No. So they used actually 10 to the 10 slated determinants to get the full CI calculation. That means you take all the slated determinants they can generate from the given basis set. And you can see most of them don't really count. So what we do now is to use neural networks to select out what are the slated determinants that really count. And this is a collaboration with Professor Philip Hansmann in Erlangen. And we have had a great deal of fun with this. Well, one paper has come out already this year. Here we calculate the full dissociation curve for N2 and get it very good agreement here with experiment. So basically it works in the following way. So let's say we have a pool of slated determinants. We take a random sample from that, do a calculation for that much smaller set of slated determinants, see what the coefficients are, which coefficients are large and which are small. We feed that to a neural network and we then apply and train that, and then we apply that to the large set. So that's how it works. We never do a configuration interaction of a very large set. We do several on smaller sets to train the neural network and then apply that to the larger set. And so basically, the neural network gets in the string of occupation numbers for the molecular orbitals and then uses a convolutional filter. And then in the end, it says yes or no, depending on whether it thinks that this slated determinant should be included or not. All right, so we now do this for the Rydberg state, for instance, here of ammonia. And now we do the Hartree-Fock calculation actually for the Rydberg state. So we're not using ground state slate determinants, but rather the excited state slate determinants. And we can get this value here. So this is indeed then the best estimate that we have, which is very close to the experiment and close to the density functional calculation results. This is now on arXiv. Okay, and then just very, very briefly, we apply this also to other molecules. Here's a calculation of propane. The largest configuration interaction calculation to date was done by Fujitsu last year. They wanted to show how Fujitsu computers could do the most amazing calculation for propane, 10 to the 12 slated determinants. And we reproduced that with 10 to the 5. And go beyond that. So the white line here is actually the configuration energy, the correlation energy obtained by the Fujitsu, and then here we have the a larger configuration energy, actually correlation energy with 10 to the 5 slate determinants. So it reduces the number of slate determinants here from 10 to the 12 to 10 to the 5 by using the neural network. Eventually, we want to do calculations like this. We have an embedding cluster here where we do high-level calculations of molecules binding to a surface, let's say, or absorbing on a surface, embedded in DFT, and then couple this to a semi-infinite solid with a green function matching. Anyway, so let me now just acknowledge my coworkers. So here's Alexei, which I mentioned before, and you saw he was heading towards the peak of the mountain here. Now we're standing pretty much on the peak of the mountain. This is Benedict. He did some calculations of chromophores in solvated solution. I didn't talk about that. Jónsson has been a long-term collaborator of mine. He is really the person in charge of the GPod development in Iceland. And Gianluca Levi was a postdoc and now is an independent researcher. He got this ERC starting grant last year and has moved to Trieste. But he is the one who really got us going on to excited state calculations, which I thought I would never do. I was really happy on the ground state. And I thought, excited state is just for specialists in quantum chemistry. No. All right, so he got me into this, Gianluca Levi. All right, so here are other people. I mentioned already some of them. Jörg is now working with headquarters in Mulheim. Dagrun was a student, bachelor student, did some of the Rydberg state calculations. She's a student here at EPFL now, doing her master's degree. And then here's the group from Erlangen and Professor Philips Hansmann. Marta was a postdoc. She's now continuing to work on this with us. She's now in Nicolaus Copernicus University. And then a group in Peking University has been doing the last work on the with the hybrid functional on the nitrogen vacancy defect in diamond. Okay. And then here, finally, I'm just going to leave this here for a summary and conclusions. But this is the picture taken almost on top of the glacier at midnight, pretty much. You see, in Iceland, the clock is kind of funny. Our clock is 1.5 hours wrong. And so the lowest position of the sun is really at 1:30 in the morning. All right, so thank you very much. I'm happy to answer any questions.
Thank you, Hannes. That was wonderful. And, I always love the approach of, asking the right question and finding the simple solution, I think.
Okay.
So open, I was going to ask, if anyone has fallen into the volcano, but we'll discuss later. So please, you can.
So I have wrap my head around is every time you do these methods that follow eigen modes by flipping the gradients along some directions, you sort of don't have you're doing a search that doesn't have a well-defined
object function.
Yeah,
that's right.
Is this something that you have, since this is your bread and butter, do you understand what this means, what this implies, and so this is not a problem?
Okay, so if you're using a method that requires a line search, which you really should do, okay, in conjugate gradients or LBFGS, you can't really do the line search.
Yeah.
Because you don't know the value of the object function. You're doing messing with the gradient and you don't know what function differentiated gives you that gradient, right? And so you have to do the line search in a different way or skip the line search.
But is there some fundamental reason why it is not possible to do a saddle point search that is based on the definition of an objective function?
I'm sure it can be done, of course. Yes, it can. There are all kinds of other ways to converge onto saddle points. This is the one we find most robust. And yes, okay, so we're living dangerously. We don't really know what function we are differentiating, but who cares? I mean, you want to find a function for which the gradient is 0. You want to find a point, sorry, for which the gradient is 0, and so you work with the gradient.
Okay, I'm into that.
Okay, good point. Though.
Thank you for the beautiful talk. I was a little bit lost about the DFT and the wave function method. So we have seen the example of the lithium MgO, where we saw that if we consider the self interaction correction, the gap could be very well corrected. Mm. But in the very last application, we also saw that for the full configuration method, it doesn't work very well. So
for the configuration interaction method?
Yes, right, because we are seeing a high error bar comparing with the experimental result. So
no. So sorry. Yeah, no. I think there's a mistake, a misunderstanding here. So,
sorry.
So this is the result from the configuration interaction, selective configuration interaction. This was just pretty good. It's much lower than this extrapolated full CI that we were worried about.
I see.
So here's the neural network, selective CI calculation, where we start actually with the Hartree-Fock optimized for the 3PZ Rydberg state. And we include, 10 to the 4 late terminals or something like that. And, it agrees very well.
Okay, I see.
The problem here with this calculation is this basis set. It's an atomic basis set,
I see.
which doesn't have long enough tails to represent the large distribution of the electron.
Okay.
And you know what happens when you confine a quantum state? You would raise its energy, right?
Yes, right. Yeah.
And
I
so
see.
it's too high.
Okay, so problem.
And still it's
Yes.
augmented, but you really to get the Rydberg states with atomic base sets, you have to have much more diffuse functions. So there are ways to put a D here in front, and then it actually works out reasonably well.
Okay, thank you very much. Got it.
But it's really good to have just a condensed matter code, plane waves, real space grid. You don't have to worry about any of that, right?
That's true.
Thank you very much for the talk. So my question is a follow up on the first question you received. So I also have doubts on the correction of the gradient. So my question is more about your opinion. So what do you think about using this type of method when you are in when you use functions which are not depending only on the density, but more advanced functions which are also depending on the Green's function? Do you have any sensitivity on this type of approach in order to find the saddle point? And maybe another question related to the initial state. So you didn't mention the initial state position, but I guess when you go in higher dimensional spaces and you have an higher dimensional manifold to explore, it's also the number of saddle points becomes really high. So you have to position yourself in the right point. So I would like just to hear your opinion on this.
Okay, yeah, very good. So there are two questions there, right?
Yeah.
So coming to the gradient, I mean, no matter what method you're doing, I mean, so for instance, we go here and use Purdue-Sunger self-interaction corrected functionals that are they're not just simply total density dependent, they are orbital density dependent. I mean, anyway, you have some degrees of freedom to describe your wave function or density, and you have some way of calculating the gradient of the energy with respect to those degrees of freedom, no matter what level of theory you're doing. You have to, right? You have to somehow be able to optimize your wave function so as to get to the ground state or something else, right? So most methods then involve calculating the gradient of the energy with respect to your degrees of freedom. That's the gradient I'm talking about. Should always be there. The second question was the initial state. Yeah, so as I said, we have to, this is in a very high dimensional space. I mean, we are having here many degrees of freedom, right? We have a basis set, this is a plane wave or a real space grid. We have enormous number of degrees of freedom. There's no question about that. We're not just working in two-dimensional systems, And so the key thing here is that we do the ground state calculation. We decide what excitation we're interested in principle. And so here it turned out, it seemed like a HOMO-LUMO excitation, but that takes us from the electron from the right to the left. But then we do that promotion, freeze those two orbitals, relax all the other ones, and then do a calculation of the eigenvalues with Davidson. Davidson is a method that's similar to Lanczos. It's an iterative method. You don't have to evaluate the Hessian matrix for sure. You don't want to do that. There's an enormous number of degrees of freedom. Just evaluating Hessian matrix would be crazy, right? But there are these iterative methods like Lanczos, and Davidson is a preconditioned Lanczos method. So you just do some iterations. You converge onto the lowest eigenvalue first, and then the second lowest, and the third lowest, and so forth, right? And you get eigenvectors corresponding. So this is how CI configuration interaction calculations are done. Davidson was a chemist and is a chemist, right? And invented the Davidson method to solve big CI problems, with millions of degrees of freedom. So that's how we get the starting point. And from that on, we let everything loose. But we have to decide, what's the saddle point order? Here we estimated 7 negative eigenvalues. One of them actually rather close to 0, within 1 eV. So we searched also for 6, and it turns out this particular transition was a 6 or is a 6th order saddle point. So, but this is all within a very large space. I mean, your question was somehow, how can we home in on the right region in this very large space? And so that's the way it is. We start with the ground state orbitals and the orbital energies, decide basically what transition we want, then try to go as close to that as possible by freezing the orbital we take the electron from, freezing the orbital the electron goes into, relaxing everything else, allowing the system to respond to this, and then hopefully we're close enough. All right.
Two last questions. When you
position about the order of the saddle point that you are targeting for specific excitation. So I was wondering, where does this intuition come from? Is it for this kind of very challenging excitations like charge transfer excitations, which we know that fail miserably time dependent?
Yeah, but so it's more the opposite in a sense from what you said. We say, here's an orbital where the electron is on the right-hand side. And here is an orbital where the electron is on the left-hand side. So let's go and let's try to engineer this transition. And that, okay, turns out to be from the HOMO to the LUMO, but that's a secondary issue. And once we say, we want to get this, let's take the electron from here, put it there, freeze those two, and then calculate how many negative eigenvalues the Hessian has. So it starts by saying, here is a qualitative feature. I want to move the electron from right to left.
It does not require feeding in a priori an order for the sample.
No, not at all. That comes afterwards. That's at the end of this procedure. We say, there are 7 negative eigenvalues, but let's guess, 8 or 6. Let's do all 3 calculations. Turns out to be 6th order. Okay, but that's the weakest point. We need to know that saddle point order. We need to guess it. So, but we need to try here 3 different calculations. Yeah.
Hi, Hannes. Great talk as usual. But
he's a student of mine. He's a former student of mine, working now with Mikael as a postdoc. So
yes,
he's going to ask the hardest question.
No, it's about the neural network and what goes in and what is being learned there exactly. I'm a little unsure about how that's working or what it's doing.
I must say I am also.
Okay.
How does a convolutional neural network really work? I was hoping you would tell me. You know much more about machine learning than I do. It's a mystery to me, really. I mean, I can tell you operationally what happens, right? In goes these strings of occupation numbers for the molecular orbitals. One for the molecular orbital being occupied, here spin up and here spin down, right? And this is the string that is fed into the neural network, the convolutional neural network. And it recognizes patterns for these straight determinants that get a large coefficient in these test calculations that we do. We do these full CI calculations on a smaller set of straight determinants and decide, okay, these are good, these are not good, train the neural network, and then apply that to the larger set. And so, but don't ask me exactly how it works.
Okay. Thank you.
You did actually, but I refuse to answer.
Hannes,
but we use JAX, so this is Google technology. Right, sorry.
No, this was wonderful, and really loved every bit of it. Professor Jónsson will be around at least until 4 o'clock. So, I mean, in the sense that we have the defense at 4. But if people have more questions to ask and we can take them, I mean, you are very welcome. And if not, thanks again to everyone.